Hi everyone, I'm Patsvi Manakun, and in this talk, I'm going to present the paper Abstractive Spoken Document Summarization using Hierarchical Model with Multi-Stage Attention Diversity Optimization. In this work, we look at the problem of generating a summary for spoken document, such as meeting recording using neural networks. Spoken document summarization pipeline includes an automatic speech recognition or ASR system to convert from speech to transcript and a summarization system. There are two types of summarization approaches. The first type is extractive summarization, which selects and reorders words or sentences in the original source document. The second type is abstractive summarization, which generates words or phrases that may or may not appear in the original source document. In this work, we focus on how to build an abstractive summarization system for spoken documents and the impact of ASR on summarization performance. The challenges in spoken document summarization are, firstly, spoken documents such as meeting transcripts tend to be long, contain redundancies, less grammatical, and less well-structured compared to written text. Secondly, the data available for developing system is not large, resulting in generated summaries being quite repetitive, as the model does not see a diverse set of examples. Thirdly, in practice, transcripts are derived from an automatic speech recognition system, and even the best system makes errors. Previous work has shown that hierarchical architecture performs better than standard RNN architecture, including the pointer generator network. Standard RNN has information flow from the first time step to the last time step, and due to long input sequence of spoken documents, it was found that the standard architecture is less efficient. The hierarchical model encodes the input sequence using a gated recurrent unit or GRU into vector representing words, and then another GRU to encode these vectors into utterance representation as shown in the diagram. Attention mechanism is computed at both word and utterance levels for the decoder to make predictions. Utterance level attention mechanism is crucial for long input sequences, and based on this attention, we propose a measure of diversity for the attention mechanism. Our notation is alpha UT denotes the attention vector over utterances at decoder time instance T. Tk denotes the number of words in utterance K, and K denotes the number of utterances in a document. We then define two attention diversity scores. The first one is intra-sentence diversity, which measures the diversity or the variation of utterance level attention in an output summary sentence. The second one is inter-sentence diversity, which measures the diversities of average utterance level attention across all output summary sentences. Both of these diversity scores are shown on the slide. I have defined two attention diversity measures here, motivated by the fact that we humans are likely to attend over the same input utterances when producing one particular summary sentence, but we attend over different input utterances when producing different summary sentences. This translates to low intra-sentence diversity and high inter-sentence diversity. Hence, we propose a diversity loss to be optimized in addition to the maximum likelihood criterion during training. And the diversity loss is defined as the ratio between intra-sentence diversity and inter-sentence diversity. In addition to target summary information, our spoken language dataset contains dialogue act and extractive summarization information. Dialogue act describes the type of an utterance such as statement, opinion, acceptance, yes/no question. In this work, there are 15 classes of dialogue act. Using the vector representing utterance I encoded by utterance level GRU, we add a linear layer with softmax activation function to predict dialogue act. Furthermore, utterances are labeled as being salient or not. This can be thought of as extractive summarization. Similar to dialogue act classification, we add another layer but with a sigmoid activation function to perform extractive summarization. The complete loss function that we minimize during training includes: the first one is the maximum likelihood criterion that given the reference target summary, we try to make prediction as close to the target as possible. And this criterion is the main training objective for abstractive summarization or in any sequence-to-sequence task. The second criterion is dialogue act classification and extractive summarization losses. These losses are maximum likelihood based that require additional annotations. The third one is diversity loss, which is the ratio between intra-sentence diversity and inter-sentence diversity. It should be noted that minimizing the diversity loss is equivalent to encouraging more attention diversity at training time. Having described the process at training time, we now look at decoding method. Teacher forcing decoding is used during training and it requires target reference. However, at test or inference time, free-running decoding is used. Free-running decoding relies on its own prediction. As a result, diversity of output prediction and attention mechanism decrease. In order to mitigate the difference between teacher forcing and free-running, we propose a simple modification to free-running by penalizing repeated unigrams, and we call this decoding method unigram bias decoding UB. Note that better term in the expression on the slide is the unigram bias penalty parameter, and that the higher the value is, the more penalizing effect. In this work, we carried out our experiments on the AMI meeting corpus, which is a spoken language data, and CNN Daily Mails, which is a commonly used dataset for text summarization. Note that compared to the CNN Daily Mails dataset, the size of the AMI meeting corpus is much smaller, and the average number of input tokens is more than 10 times higher, and the AMI meeting corpus includes both manual and SR transcriptions. Now, let's dive into our experimental results. Firstly, in the table we show here, it's the diversity scores for different decoding methods. We know that teacher forcing is better than free-running in terms of summary generation. And when looking at the diversity scores, it can be seen that intersentence diversity drops, while intra-sentence diversity increases when swapping from teacher forcing to free running. However, when we use unigram bias decoding, inter-sentence diversity can be increased. The figure shows both diversity scores relative to free running. As beta increases, the result shows that intra-sentence diversity only fluctuates, while we can improve or increase the intersentence diversity by increasing beta. But the improvement also plateaus once the beta value is high enough. Now, we look at the summarization performance on the AME meeting corpus using our approach. Firstly, we compare the results when we train the model on just the maximum likelihood criterion denoted by just HIER, higher, and other settings include multitask learning objective and diversity lost. We vary the value of beta or unigram bias constant and report the optimal values in the second column. It can be seen that better summarization model requires lower value of beta, suggesting that better models are already more diverse. Another observation is that multitask learning objectives improve summarization performance, and explicitly optimizing the diversity loss use a better summarization model. We achieved our best model by training on our objectives, and this model requires the least unigram penalty or beta at test time. We also investigate the impact of ASR, and our conclusion is similar to other previous research that ASR has lower impact on summarization tasks, and at around 20% with error rate, the summarization performance is only around 1 in root score lower than manual transcription. In conclusion, hierarchical model performs better than standard and in architecture for long input sequence spoken documents. Hierarchical structure allows multitask learning that improves summarization performance. Our attention diversity score correlates well with summarization performance. And by explicitly optimizing the diversity loss at training time, we achieved a better summarization performance. Unigram bias decoding increases diversity score and yields a better summary output. Thanks to Cambridge Assessment, University of Cambridge for supporting this research. And thank you for your interest in this talk, and feel free to ask any question. Thank you.